Okay, so now we get to the problem that really messed me up as a student, which is the electric field from a ring or a line of charge. Now, if you can tell from my picture, you guys know I'm not an artist, so deal with me here a little bit. We have this ring of charge, and imagine that that's kind of in the horizontal here, out in front of the board. We have a total charge of positive Q on that ring. That ring is centered right here, so that's the center of the ring. And then at a distance z up from the center, at a point P, we want to figure out what the electric field is at that point P. Notice that each point around this ring is a distance r from the point P. And then we have big R down here representing the radius of that ring. So be careful there. Big R represents the radius for the big ring. Little r represents the distance from a point on the ring up to a point P. And then we have z being how far up the center of the ring is from the point P. Okay, so to figure out what the electric field is at the point P, the first thing we have to do is do our linear charge density thing again. So the linear charge density would be the amount of charge divided by some length in question. So we're going to take, again, some length element, ds, of our ring, and we're going to have to integrate that small length element over the total length of the ring in order to figure out the total electric field in this case. Okay? So each small charge element produces a small electric field element, 1 over 4 pi epsilon naught dq over r squared. Each small charge element creates a small electric field element. Now we just figured out from our last example that dq is equal to lambda ds. So now I'm going to have that d of the electric field, the small amount of electric field, is equal to 1 over 4 pi epsilon naught lambda ds over r squared. You should notice that this problem is starting exactly the same as the previous example. So that should make things a little smoother. Okay. Now here's where things get tough. Okay? This r down here is the distance from our length element up to the point P. Okay? Now that r is thankfully fixed for each one of our points on this ring. Little r is always little r. But I want to put that in terms of z and big R. It doesn't make sense why I'm doing that right now. In your brain, you're saying, oh, r is just a constant, little r is just a constant, this shouldn't be a problem. Watch what happens in a couple minutes because of the symmetry, however. That is going to impact the whole thing. So we are going to replace, because little r squared is equal to big R squared plus z squared. It's a right triangle. Little r is the hypotenuse, big R is one side, z is the other side. So that means that little r is equal to r squared plus z squared to the 1/2 power. Doesn't seem so important yet, but trust me, it's going to be. So now that makes our small electric field element equal to 1 over 4 pi epsilon naught lambda ds over, since this right here is just r and we're going to use r squared, we're going to square this whole term here, so it's just going to be r squared plus z squared. Okay? Hopefully I didn't go too fast on that. Okay, now the symmetry argument. At the point P, we are going to have one electric field coming out like this, and then another electric field from the other side of the ring coming out like that. Okay? If you think about these positive charges coming up and creating an electric field that moves like this, we have other ones on the other side that are creating an electric field like that. So again, we have very nice symmetry in this problem. So if I come down here and create something like this with our angle of theta and another angle, the same theta, with those two thetas being the same, we are going to get that the x components of those electric fields are now going to cancel out. The y components are going to add together. each one of these electric fields as we go around always has a positive y component. The x components, however, will always point in the other direction for a point directly opposite on the ring. So those x components are going to cancel out, the y components are going to all add together. So if I look at this thing right now, and again the picture is not 100% clear, so be careful here. If we think of that as being one side of this electric field line, we have the EX down here, and we have the EY right there. Notice that again, I'm going to need the cosine of this angle to get the EY. So I need the cosine of theta in order to get the EY components. But that angle is determined by Z and this R right here, the little r. This angle theta right here is the same as this angle theta here. So the cosine of theta is going to be equal to Z over R. Z over R. And now R we found down here, so we have Z over R squared plus Z squared to the 1/2 power. So I replaced the little r right here with the little r right down here. Okay? So now, in order to get the y component of my electric field, I have to multiply the small electric field by the cosine of theta. And so, I'm going to have 1 over 4 pi epsilon naught lambda ds over, now be careful here, as I be careful here and watch my work. This is going to be a z up top from the cosine of theta, the z right up here, over, now we have this r right here to the 1/2 multiplied by r squared plus z squared right down here. So it's r squared plus z squared to the 3/2 power. So this is going to be z squared plus r squared to the 3/2 power. That's what happens when we multiply by the cosine of theta. Cosine of theta was z over little r. I had in this original part r squared plus z squared. So now I need to multiply this by z over r, so this goes to r squared plus z squared to the 3/2 power, and I have a z up here in the numerator. Now what's made this very, very nice is I'm just integrating over the arc length, correct? I could have integrated over the angle theta, but that would have been absolutely terrible. I believe that would probably be cylindrical coordinates, wouldn't it? Because you'd be going around in this kind of way with some r. Or maybe it's spherical polar. Whatever the case, I want to avoid that. And in the previous example, we didn't know the exact arc length in question. We could have figured it out from the 60 degrees to the lower 60 degrees on the previous video's example. But here, I know what the arc length is of this circle. It's the circumference of a circle, right? 2 pi r. So my limits of integration, if I'm integrating over an arc length here, ds, is 0 to 2 pi r. So to get the total electric field, we are going to integrate dEy, and that's going to be an integral from 0 to 2 pi r of 1 over 4 pi epsilon naught z lambda ds over z squared plus r squared to the 3/2 power. Now when you do all that work, we now have that the electric field is equal to z lambda 2 pi r divided by 4 pi epsilon naught z squared plus r squared to the 3/2 power. So again, just replacing ds with 2 pi r. Then they want to make it look nice, so they do a little bit of math to it, and they're going to make qz over 4 pi epsilon naught z squared plus r squared to the 3/2 power. Now notice what they did here. They went back up here and they said, okay, lambda is equal to the total charge over the total length The total charge was Q. The total length of this whole thing is the circumference, 2 pi r. So then they replaced lambda down here with Q over 2 pi r. The 2 pi r's canceled out. So you were left over with Q and Z over 4 pi epsilon naught Z squared plus R squared to the 3/2 power. Okay? Now think about what happens if we increase this distance. Okay? If we get further and further away from this ring, what's going to happen to the electric field? Now your brain tells you it's the exact same thing as what happens when you move away from a planet in terms of the acceleration due to gravity. Eventually it's going to go to 0. Let's see if that works here. If we continue to get further and further away from the ring, the Z down here is going to grow. The Z down here is growing faster than the Z up here. So eventually, if we took the limit as Z approaches infinity, we would get that the electric field goes to 0. So we did it correctly. Keep this answer in mind. We're going to use that on the next video to start with a charged disk. So something that is solid here, not just a ring of charge. It adds one complication to the entire problem, which we can deal with, but it's easy if we start off with this solution down here.